On the bench today we have the Fuzz Face. It's one of the oldest pedals. It's got a very simple schematic, but it's very hard to use, so we're going to break it down and show you how to use it with a buffer, show you how to gain stack it, and show you how to get some great tones. One of the wonderful things about the Fuzz Face is it gives you the ability to control the distortion or the tone of the pedal by using your volume control on the guitar. Here's our clean tone. Now let's engage the pedal. And now I'm rolling off the volume. So as we play, we can control the level of distortion we want and go from this clean sound to distortion and back. Depending on how we want to express ourselves. Now we're stacking the super overdrive in front of the Fuzz Face, and I'll just turn the Fuzz Face on. Even without the pedal being engaged, you can see this has started to splutter. Some might say it's a cool sound, but it's a very spluttery sound and not the true Fuzz Face sound. Even without engaging the pedal, that's because all bus pedals have a buffer. And it's the buffer and the impedance mismatch of the output of this and the input of this that are causing that splutter, not allowing us to gain stack. So what we're going to do is look at what we can put in between here, the output of this pedal and the input of this pedal, so we can gain stack and present to the Fuzz Face a signal that it likes and that is expecting, and allow us to do all the cool things that we could do with the volume. And that's another thing. If I just... What you didn't see there is that I was actually turning the volume up and down and the signal was the same, and that's another effect of this buffer. So what we really want to do is bring some expression back into the signal path, so when we adjust the volume we can get the great tones that we expect out of the Fuzz Face. So let's go ahead and do that and look at essentially the guitar electronics that create this great interaction between the pickups, the pots, the cables and the input. Let's refer to the Electro Smash webpage. And this is the Fuzz Face analysis, and let's just scroll down. It's a very simple schematic, 2 transistors, a lot of gain, and that's how it creates the distortion. Well, a lot of gain combined with only a 9-volt power supply, so not much headroom, so it distorts. But we're really interested in this section here called the Fuzz Face input impedance. So it's 8K. Of course it's nominally 8K because impedance is a function of frequency, and as we get into how we studying the guitar circuit and how pickups work, we'll understand what that all means. But essentially, if you look at the input impedance of a modern pedal or a buffer, that input impedance is more like a megaohm or 3 megaohms or 2 megaohms. So it's very high, it's in the millions, not in the thousands, which is what 8K is. And it's that interaction where you've got a guitar that, say, nominally, again, I'm going to always just use the word nominally, the resistance of the coil is, say, 10K. So you have 10K going into 8K. That's a certain voltage transfer. If you've got like 10K going into a 1 meg, that is another type of voltage transfer, and it's a better voltage transfer than this. And so when you play your Fuzz Face, and you modify the output of the signal or the impedance of the signal or the impedance / resistance with the pot, then it's really going to affect how this circuit works in terms of gain, because you're actually varying what like a resistor set here, if you will. It's actually an inductor, resistor, capacitor set here on the front of the circuit, and that changes totally the gain characteristics of this. Now, if you put a low impedance input into here, which is what is typical of a buffer or a modern pedal, that again really affects the gain of this pedal, and it completely goes into overdrive, and that's why you get the splutter. To understand how the guitar interacts with the fuzz face, let's start with the pickup. So this creates an electrical signal that comes out on these two wires. Essentially, these are magnets here, and we have a metal string that vibrates, that induces an EMF. We have a coil that's wrapped around the magnets, and that EMF that's induced creates current that flows out of these wires, alternating current. Now, there's three circuit elements to this device. One is, first of all, it's a long coil of wire. So the longer the coil of wire, the more wrapped the pickup is, the bigger the resistance is, because there's more wire. Secondly, any kind of cable or wire that's wrapped like this has an inductance, and so we have inductance. And then secondly, you can see inside there's lots of wires, and they're all very close together. And that closeness creates what we call a capacitance as well. So we've got three elements. We've got resistance, we've got capacitance, and we've got inductance. So let's draw that up on a schematic now. We have the string. Just going to draw this as a vibrating string. If you look closer at a string, it would look like this. And then we have the inductance. That's a symbol for an inductor. Then we have the resistance. And then we have what runs in parallel with the circuit, the capacitance. And this is going to be in the region of, say, 8 henries, 4 or 8 henries, depending on the make and type, and we'll get into that. This is going to be 7 to 15k, again depending on how wrapped the pickup is, and this is going to be a small nanofarad value. And then this actually then connects to your volume pot on the guitar. So the job of this is to short circuit this back to ground so you don't get any current flow. And then we also have another element usually, which is another pot that goes through a cap, which creates a high pass filter, so all the high frequencies go down to ground depending on where you have this. And then this goes to the outside world, to the jack, and then that connects to your fuzz face. But it connects through the fuzz face actually through a cable, and the cable electrically is similar. It has a resistance and it has a capacitance. And the longer the cable is, the bigger this capacitance is. So the longer the cable becomes, the less higher frequencies will pass through the cable, and they will be passed more down to ground and attenuated. And that's one of the reasons why we use a buffer, is to eliminate the effect of the long cable and produce a much brighter tone. Now let's draw out the theoretical performance of the pickup. We're going to have a vertical axis here, could represent amplitude or impedance, and then we're going to have this axis here, which is going to be frequency. So we'll call that amplitude. We'll call this one frequency. And there's a few components to this. So if I just draw this dotted line across here, that's constant all over frequency, that's your R, that's your resistance. And then your inductance has a curve that's typical like this. And then there's a reciprocal curve, so that's the inductance. I did I, so let me just say induct, so we don't confuse it with current. And then we have a reciprocal equation that gives us the capacitance performance, the amplitude due to capacitance over frequency. And then this point here where they cross, that is the resonant frequency, R. And that's very important because all pickups and all guitars have a resonant frequency, and that is a big contributor to tone. If we look at some resonant frequency curves, a single coil Strat profile like that, and so this is high in frequency, so it's kind of a sparkly sound. And then if we look at pattern applied for inductance curve, it kind of looks bigger and like that, so you get a more beefier beefier sound because these are lower frequencies. So what we need to do is present this type of impedance variation, or this impedance profile, to the fuzz face, and also be able to use it with a buffer. Looking around the lab, I have a few inductors here. These are transformers, but it's a coil of wire, so it's an inductor, so we just use one side. This is one from a wah-wah Fastell. This is in the millihenries, and so we're looking for something more like 8 henries. These two might be better candidates. This is 600 ohms impedance, and this is 10k impedance. So this one looks like something that might be a better approximation to a guitar pickup. So I'm gonna use this, and we're gonna look at how we would now place that with a buffer. So here's our design. So we're gonna have input. So this comes from the guitar. We're gonna have the buffer. Draw it like that. Put a B on it, so it looks like a buffer. And then we're going to do the pickup emulation. So we'll have an inductor, we'll have a resistance, and we'll also have a capacitance. In fact, we're going to have 2 capacitances. And then we'll have a switch, which goes to ground, and the other side of the input goes to ground, and then the output also goes to ground. So that's in, that's the guitar, and that's out. And so I had some boards built. This is one in its raw form. So this is power supply filtering. There's the buffer there, and then these are the resistors that either set up the 4.5 volts that we need to bias this guy, and also the resistance value here. And then what I did in the design, and this is where you would place the transformer, and then I didn't do these 2 capacitors as a surface mount. I did them so people can change them, because this is how we're going to move the curve around for the pickup responses. So if we remember, our pickup has resonant frequencies, that kind of look like this. So this is a path, and this is a single coil. And so by messing with these capacitance values in the nanofarads, we can change the characteristics of the guitar signal that we're trying to emulate. And then this here would then go maybe to an expression pedal. So I'll put that in there. So we can use the pedal to emulate the guitar volume pot, and then this would go to the fuzz face. Fuzz. I've made one up here, so this switches it on and off basically. So this is like a bypass, and it's a buffered bypass, by the way. So when it's in, it's an inductive buffer. When it's out, it's just a regular buffer. And then S and L is for our single coil, and single coil, and L was for long cable actually. So when I originally did it, I was going to do small cable and long cable, instead of doing it more correctly, I believe, by having it as more of the resonance, by modifying the resonance of this circuit to emulate the different types of pickups. And so here it is inside. So you can see there's the transformer mounted, and there's the those two little red Weimer caps there, because these are in the nanofarad values there, so you can switch between the two. So why don't we now actually do a frequency response test of this and see where our resonances lie. Now I've got the scope hooked up, and I'm going to do a rough frequency response plot. And so the inductive portion is out now, and we're at about 300 hertz. So let's increase that. 400, 500. And I put the 2 cursor lines on so we can see if we're exceeding those 2 lines or attenuating between those 2 lines. Now we're at 3.6 now, so I've been going up. It's about 4 kilohertz. So I'm just going to declare that flat. Now I'm going to engage the inductive part. Okay, so low frequency, no change. And then we're going to increase the frequency, 100 hertz at a time. You can see now we've exceeded the lines. And then the signal's going down again, and it's going down quite a lot. So that frequency is about 2.6 kilohertz. And then let's try and find that peak again. I'm going down in frequency. And so the resonant peak there is about 1.5. So it kind of goes flat, then up, peaks at 1.5 kilohertz, and then goes down. So I'm going to draw that in a second, but let's put it to the switch, this switch in the up position. Increase the frequency again. And there we saw a peak. A peak at 2.1 kilohertz. So that's quite cool. Let's sketch out what we saw. Frequency, F, and the response, this is amplitude. With the filter in, with just the buffer in, it's just a flat line. With the inductive element attached, so when the switch was in one position, let's say this is 1 kilohertz, and this is 2 kilohertz, kind of a linear scale. And so we saw this, the switch in one position, and with the switch in another position, we saw this. So these are the two resonances that we are trying to create with this circuit. So I think that's not bad, and that could represent two different circuits. But I made the circuit so you can actually replace the capacitors and move these resonant frequencies around. All right, let's plug it in and do a tone test and do some experiments using the guitar. Now we've got the inductive buffer hooked up to the Fuzz Face. It's currently acting just like a buffer, and we've put Fuzz Face's worst enemy as well, a boss pedal, in here, but this buffer is going into this, buffer is going into this. So if we have it just as acting like a regular buffer and switch it on, a lot of splutter. So let's switch the inductive buffer on. Sounds fantastic. This is my modified boss pedal, so it's with the switch in the down position, it actually avoids or bypasses all the distortion circuit, but I get a chance to use this fantastic EQ, parametric EQ section. So I'm going to put it in. Acts like a cocked wah. Well, that's fun. So now I can do some equalization up front and have it work with all the buffers. But my volume switch on the guitar has no effect. It just turns it down. So there's no real tonal effect. So what I'm going to do now is put in between these two an expression pedal and see what the tones are like then. I've got my vintage expression pedal now in the circuit, so this is acting like a guitar volume, and the volume is down now. Just add a bit more volume. So it's not fully attenuated. way down. So we get the full fuzz effect. Up a bit. So we're modifying the impedance that the fuzz face sees, which is fantastic because now we've isolated this circuit here from the rest of the pedals. Like the boss pedal with all its buffers and everything is now isolated by a buffer in here, and then the inductive element, the inductive capacitive resistive element that we added. Then we can use this to give us full expression now with our feet as opposed to using our hands and the volume pot, and that allows us to get the most out of our fuzz face tonally. Fantastic. Now I've stacked a super overdrive in front of the inductive buffer. So that's with the pedal off. Now I'll engage the pedal, and the idea here is that I've got the gain set low down, and so this is kind of acting like a boost with a bit of distortion. But I'm really interested in the filter effects of this thing because it emphasizes the mids. So if I just press it in now, so you can see I've created a filter where I'm just peaking on the mids that takes out some of the lows, that the low frequencies that's inherent in the fuzz face design. So that's it. So we've done a bit of pedal stacking, we've isolated the pedal with a buffer, we've a volume pedal, expression pedal to act like the volume on the guitar, and the fuzz face is just the fuzz face. Thanks for watching. Please like and subscribe.